Welcome to the video regarding the first bullet point in the 4 bullet points in shape and space measurement, specific outcome number 1 for the 2016 revision of Alberta's grade 9 curriculum. So there are 4 bullet points, each of which will get its own video. And the first one is solving problems and justifying solution strategy using the following circle properties. The perpendicular from the center of a circle to a chord bisects the chord. This is what we are going to prove today. Before we can do that in a reasonable manner, we need to define our terms. So a chord is any line connecting 2 points on a circle. So for any given circle, the largest possible chord will be a diameter going from one side to the exact opposite side. But that is far from the only possible chord. So in the case of a circle, a chord connects one point to any point anywhere else on that circle. Going straight through the center gives us the diameter, but it could be any of these points here. Anywhere at all, that line is now a chord. So that is one of the 2 key terms that we need here. The second key term to review is a bisector. So in algebra, a bisector is a line that divides a geometric object. I say object because it could be a shape or an angle. So it's something in geometry, and it's divided in exactly half. So what we are going to prove today is that if you take a line from the center and draw it perpendicular to absolutely any chord in the triangle or in the circle, if it's drawn perpendicular, it will also be a bisector. That's what we are looking to prove today. So let's use a more precise tool than the whiteboard and my hand to draw our circle. And the GeoGebra geometry tool puts one point automatically on the circle. Our chord is produced by putting any other point at the end of that. So connecting one point on the edge to any other point on the edge. And we're going to be working with a line perpendicular to that chord, which passes through the center of our circle. So we know we can build a perpendicular line because from any point you can find that perpendicular line. What we need to prove is that once we have done so, this line is bisected, which means it's divided into exactly half. That is the piece that we are going to prove today. And again, because this is intended not so much for grade 9 students, but more for Math 20-2 students who want to review grade 9, because this is the next time that they see that grade 9 content, is in Math 20-2. We are focused on the 20-2 approach, where there's more emphasis on the proof and a little less on the problem solving. Although both of those elements show up in both courses, just not in the same proportions. So one piece that we are going to do to set this up is to add a couple other segments. One from the center of the circle to one endpoint on our chord, and the other from the center of the circle to the other endpoint on the chord. And I'm sorry, we do have the ability to move these points a little bit. But as we move them, GeoGebra will update all the other lines. So it keeps the perpendicular perpendicular and passing through that center. We just need to prove that after doing so, we still have, or we will have, an exact center. So we can draw this any way we want. We can even rotate about a point. So if we take a point, we can rotate the entire object around that point. And that'll be true for anything in this shape. So if we highlight everything, we're going to rotate, say, clockwise by 45 degrees, and that moves everything, although I see now it clones a different shape, which is not what we wanted. So let's get rid of that. Sorry. Probably should have played with this new tool more before I started recording. A little bit of growing pains in the video. But ultimately our goal is to show that the perpendicular from the center through any chord bisects that chord, just as a reminder. So we're going to be able to do that by building this triangle. If we can prove that this half is equal to that half, we're done. And if we remember the ways to prove that triangles are similar or congruent, we can do that by showing that we have either side, side, side congruence if all three sides are the same, angle, side, angle congruence. If two angles and a side between them are the same, then the rest of the triangle is the same. Side, side, angle. If we have the lengths of two sides and one angle, never angle, side, side, always side, side, angle. Or we could have angle, side, angle. If we have two angles that are the same and the side between them, or finally, side, side, angle. If two sides are the same and one of the angles between them is the same, then we've proven that those two triangles are congruent. It's actually the side, side angle approach we are going to use here. So let's set that up. And this is not going to be quite as precise as GeoGebra, but I find it's easier on the whiteboard sometimes to have the ability to label things and do the algebra right next to it. So we are going to do a sketch of our diagram here. It's not as precise as the GeoGebra version, but it'll get the job done. So our points are A, B, and C. And what we know is that this line came down perpendicular. So we have an angle here. So if we can do side-side angle, then we can prove that these are the same. If we prove that these bottom sides are the same, we're done, because that's the ultimate goal of the proof. That's the trickiest one to prove. It is easier to show that the other sides are the same. So these two sides are going to be the same because they are each a radius of our circle. Both of these lines go right from the middle of the circle to a point on the edge. Middle of the circle's A goes to B, which is a point on the edge. Middle of the circle's A goes to C, which is a point on the edge. Therefore, these two lines are both the radius of the circle. So that's one side. Right? We are looking for a side-side angle congruence. We now have the side because they each have a radius. We can claim an angle because this is it's a perpendicular line. It will have a 90-degree angle on both sides. So we have 90 degrees available on both sides of that bisector or that line. I'm getting ahead of myself. We haven't yet proven it's a bisector. I shouldn't be calling it a bisector. And finally, this line here is shared between the two triangles. So that is a height h. And it's one side used by both triangles. So now we have two consecutive sides and the angle following. That gives us our side-side angle once we have length h. This proves the triangles are congruent. If we wanted to, we could take it a step further and show that these two corner angles have to be the same because it's an isosceles triangle. So these two corners plus this center angle A add up to 180. Divide that all by 2, and we've got one of these corners plus half of the central angle add up to 90. You add another 90 because we have that corner, and we've proven then that these three, which would add up to 180, have to have bisected this angle as well. And if these two angles are the same, then we can do angle side angle. That's a slightly longer proof. I mention that only to illustrate that there's rarely only one way to do a proof in mathematics. What we have here is that side-side angle setup. These sides are the radii. The shared side is a height we called h. And then we have 90-degree angles for the shared angle down here. We could do that height r and then this angle if we wanted to. Again, because it's an isosceles triangle, but that is not necessary. We have our proof. Therefore, these triangles must be congruent. So whatever length this is, that must be the length of our third unlabeled side on the other triangle. Therefore, these two lengths are the same. Therefore, this line through the center bisects this angle. We can see that if we delete that line we had, and instead of taking any perpendicular line, we specifically take a perpendicular bisector of this line. We click on it, and when it adds that bisector, we see it goes right through the center. And again, this is true regardless of where that point is. Remember, B here is the one we use to pick the radius of the circle. Any circle, any chord, that perpendicular bisector will continue, no matter what, to go through the center of our circle.